Yeah, hi guys. Let's continue with what we were discussing the other day and try to uh, touch all the concepts from whole concept. Check the idea of what is limiting reagent. I think we discussed the other day. Check out percentage yield of product. A lot of times when the chemical reactions happen due to some external conditions, right? Temperature conditions, or maybe other impurities present, or maybe the amount of catalyst that is supposed to be given, all of that, if it is not matching, the percentage, just a second. Right, sorry. So as I was saying, the percentage yield is about how much amount of product that is actually forming. So the actual amount of product upon the theoretical amount which you are expected, so that into 100 gives us percentage yield. What is this question? If you want to understand how the percentage yield works, check out this. 30 liters of N2 reacts with, if 30 liters of N2 reacts with 30 liters of H2, and if 25% of yield is observed for ammonia, then find the composition of gases after the reaction. Check. And you know that volume would always follow the mole compositions. So we can use that term here. So if this is 30 liters and this is 30 liters at T equal to 0, so consider there is no ammonia initially, but maybe after some time, some X liters of nitrogen is lost and 30 minus some 3x amount of hydrogen is lost to make this as 2x amount of ammonia. Got it? Now, this is what is actually happening, correct? But in case, if ideally, if you notice, what if one of them is limiting reagent, then what will happen? See, for every 1 mole, I'm supposed to use 3 moles of hydrogen, or for 30 liters, I'm supposed to use 90 liters of hydrogen, but given amount is 30 liters. So now I'm putting theoretical value. Theoretically, what you expect is that the hydrogen should be completely consumed, correct? So since this is limiting reagent, it should not be present at all. Hence, if I notice that for 3 moles, 1 mole is required, for 30 liters, how much it is required? 30 divided by 3, so 10. So out of 30 liters, 10 liters is being only used. So what is the remaining amount? 20 liters is the remaining amount. And go to the right hand side. If it is 3 liters of hydrogen, it is supposed to produce 2 liters of ammonia. For 30 liters, how much it is supposed to produce? So 30 cross 2 divided by 3. So which is 20 liters. So ideally, I should get 20 liters of ammonia as well. Okay. So here 10 liters is consumed, 20 liters is left, and here 20 liters is formed. Ideally. This is what is expected. But only 25% is present here. So which means 25% of yield is happening. So you know that the actual amount of ammonia form will be equal to percentage yield into theoretical yield or theoretical amount. So percentage yield given is 25 into 20, okay, by 100, correct? So that makes it 5 liters, correct? So only 5 liters were actually formed. So now go back to this equation here, which is was ideally, I mean, this is what is practically happening. So use that. So I can write this as 2x is equal to 5 liters. So in that case, x will be equal to 2.5 liters, correct? So therefore, how much amount of nitrogen will be left over here, right? 30 minus 2.5. So 27.5 liters of N2 will be left. And here it is 3x. So 3x as in 3 into uh, 3 into 2.5. So 7.5. So 7.5 as in 22.5 liters of hydrogen is left. And how much amount of ammonia is forming? 5 liters. So this amount is calculated based on this X amount which has been supposedly happening. Please check. I hope this part is clear, everyone. That is how you evaluate the percentage yields. Okay, or given the percentage yields, this is how you use it. Okay, so either ways it works. Clear? Done. Let's see. Next term which we need to learn is percentage purity of impure substance. This is another problem that we usually get, that a lot of time the reactant what we are taking will have some impurities in it. In case of impurities, the actual mass present in the sample is the pure form divided by the impure amount of the sample or the total mass of the sample. That into 100 gives you the percentage purity in the impure substance. Okay, let me show you with an example. Calculate the mass of HCl that is required to completely react with 0.2 grams of 70% pure calcium oxide. So in here, calcium oxide, this was given as 0.2 grams originally, but that is a sample weight. Okay. If I check out the percentage, the actual weight here, the actual weight or actual mass will be zero point 0.2 multiplied by zero point 0.7. Okay. So that makes it 0.14 grams. So this much is the weight of calcium oxide. And if I convert that into number of moles, that will be equal to 0.14 divided by 56. Alright, 56 being the molar mass. So you can see for 1 mole, 2 moles of HCl is required. So for this many moles, how much it is required? Into 2. Hence, the weight of HCl will be equal to 0.14 by 56. Sorry, this is number of moles. Number of moles of HCl will be 0.4 into 56 into 2. And what about the weight of HCl? It will be equal to 0.14 by 56 into 2 into 36.5, which is the molar mass of HCl. Got it? So now if you notice, 0.14 divided by 56, which is 0.025 into 5 into 36.5. So that's coming out to be 0.456 grams. So this much is the weight of HCl present. Okay, please check this out. I guess this part is clear. Let's do a similar one and figure out what is the percentage purity of calcium carbonate. Please try this out. See, you have 44.8 liters of carbon dioxide that is released when 500 grams of calcium carbonate sample is heated. Please check it out. So please check this out. How to get the percentage purity. Check. From here, we can realize that number of moles of carbon dioxide will be 44.8 liters by 22.4, which makes it 2 moles. Okay. And 500 grams of calcium carbonate sample is heated. Okay. So we need to find out the percentage purity. Now notice this. We have to backtrack that, assuming that the calcium carbonate on heating is giving us calcium oxide plus carbon dioxide gas. So here we have 2 moles. Okay. And if this is 2 moles, ideally how many moles of calcium carbonate must be required? So you see, for every 1 mole, I would require 1 mole of calcium carbonate. So I can write ideally 2 moles of calcium carbonate is required. Okay, which means what is the weight of calcium carbonate? It is 2 into 100, which is the molar mass of calcium carbonate, makes it 200 grams. So ideally we require only 200 grams. But how much is the sample weight that we are giving? 500 grams. So therefore, the pure component, the pure composition, the pure composition is 200 grams. The impure sample is 500 grams. Therefore, percentage purity will be equal to pure composition by impure composition into 100, which makes it 200 by 500 into 100. Correct? Okay. So that makes it how much? 40 percentage. So the sample is 40 percentage pure. Clear, students? I hope you understood this part.
No, just 1 second.
Yeah.
How do you get the impure? Sorry.
How did we get the what?
No, no, I didn't read the question properly.
Okay. All okay?
Yes, so.
Great. Let's understand this next term. Okay. This is pretty useful going ahead in multiple chapters now. So check out. This is what happens in gases. Suppose if a gas is, dissociating on its own. For example, if I have gas like PCl5, it will dissociate on its own to convert into PCl3 and Cl2. Okay, that way ammonia also at room temperature it will start dissociating into nitrogen gas and hydrogen gas. So if I consider that logic that a gas A is dissociating, and dissociation by definition itself means it should increase its number of moles. So if I take 1 mole of A, I'm expecting some n moles of product should be formed, and that n has to be greater than 1. Then only we call this process, or we call this reaction as dissociation reaction. So this is dissociation reaction. And now, suppose initially at time t equal to 0, there are A naught moles of this gas and there is no moles of B form. And as per Gay-Lussac's law, the volume of the gas, because this is not there, initially only A is there, that volume of the gas occupied is directly proportional to initial number of moles, which is proportional to A naught. But after some time t, imagine some x moles have been lost from A. So if x moles are lost from A to get dissociated, then the number of product particles should be formed will be nx moles, right? See the ratio here, 1 is to n ratio. So for x moles, it should be nx. Now what is the total moles of the gas mixture? That will be A naught minus x plus nx. This is the final volume now. So as per Gay-Lussac's law, final volume will also be proportional to total number of particles, which is proportional to this. And you know that volume is always inversely proportional to density. So if I take the volume ratio here of initial and after some time t, so I will get the mole ratio A naught by A naught minus x plus nx. And since volume ratio will be inversely proportional to the density ratio, I can call this as density ratio can be written in terms of mole ratio. But before writing that, let us understand this term, very important term, degree of dissociation. Okay, degree of dissociation alpha means how much is the amount that is lost. In this case, for instance, x is the amount that is lost by the reactant by how much was the initial amount of the reactant, which in this case is A naught. Okay, so alpha is a fraction of the amount that is lost. So that is equal to x divided by A naught. So which makes x is equal to A naught alpha. So x is equal to A naught alpha. So now instead of x, wherever there is x, I will replace that with A naught alpha. So you can see this is A naught and A naught, and here it is A naught. Instead of x, I have written it as A naught alpha. Nx, I have written it as n A naught alpha. So what you would notice is that A naught will get cancelled from numerator and denominator, and the volume ratio simply remains in terms of alpha. So it will be 1 by 1 plus alpha into n minus 1. And the volume ratio is inversely proportional to density ratio. And here is the term that I'll be using. Density after some time or at equilibrium, we will use that terminology small d. And density initially, that is before the dissociation, we use the term capital D. This is a convention used in chemistry. So remember that. So small d and capital D. So small d by capital D is equal to this value, 1 by 1 plus alpha into n minus 1 into d. Okay. So now if at all I reverse this, so I'll get this as 1 plus alpha into n minus 1 is equal to capital D by small d. And if I take minus 1 to the right hand side and take the LCM and then push the n minus 1 to the right hand side, this is the equation I will get. So alpha is equal to d minus d by d into n minus 1. D is capital D here, the first d, then small d divided by small d into n minus 1. Now, we also learned that Pm is equal to dRT for any ideal gas. So which means density of a gas is directly proportional to molar mass, molecular weight of the gas. So in that same case, if at all I take this as, you know, uh, d minus, sorry, d by d can be also written as initial molar mass divided by equilibrium molar mass or after time t. Okay, so which is also written as m naught by m of the mixture, that is mixture molar mass. So wherever there is a d by d, I can also replace this by m naught by mx, m naught by m of mix. So that's why wherever d minus d by uh, d is there, you can replace that with m naught minus m naught mix by m mix. So this is the representation of alpha in terms of molar masses, alpha in terms of densities. Okay. So if we can represent that, we can also represent in vapor density, because vapor density is just molar mass by 2. So therefore, this is initial vapor density minus vapor density of the mixture upon vapor density of the mixture multiplied by n minus 1. Okay. So these are the three formulas. Based on the data, you can use any one of them. Okay. Please go through it once quickly. Check if you have understood the degree of dissociation and how to relate with densities. Ditya, any doubt here, beta?
No, so
Manav, Dev, Kapil, all good?
Yes.
Yes.
Take it. Make a note of these formulas. Okay. So then we can start solving questions. Finished? Check. The vapor density of the mixture containing NO2 and N2O4 is given as 38.3. That means when both of them are present in the mixture of gases, the vapor density is 38.3. Calculate the moles and weight of NO2 and N2O4 that are present at that time per 100 moles of mixture. So that means initially we had 100 moles, and now we have, of course, not the 100 moles anymore, but the vapor density has observed to be 38.3. Okay. Now how we can resolve this? Check out. At time t equal to 0, initially I know that there are 100 moles, 0 moles here. At time t equal to t, we have 100 minus x moles, and we have 2x moles here. Correct? So what I can do, uh, and what will be the value of alpha, by the way? Alpha would be equal to x amount divided by 100 moles. Okay. So once again, So, so if you have 2x here, alpha would be equal to x by 100. Now notice vapor density of the mixture is given as 38.3. Okay. So which makes it molecular weight of the mixture as 2 times of vapor density of the mixture, which is equal to 2 times of 38.3. Okay. So that makes it, I'll give you, wait, give you. So 6 and then 16, 1, 6, 7, 76.6 is the molar mass at the equilibrium. But what is the initial molar mass? M naught is the molar mass of, N2O4, which is what initially present. So initial molar mass is 92. 92 is the molar mass of N2O4. Hence, I can say that alpha, which can be written as M naught minus M of the mix divided by M of the mix into N minus 1. So let's use that. So it is 92 minus 76.6 divided by 76.6 into N. How much is N? For every one molecule, you are getting 2 moles. So which means it is 2. So 2 minus 1. So that makes it 92.7. Sorry, 92 minus 76.6. Let me just calculate and tell you how much it will come. So it is 92 minus 76.6, which is 15.4 upon 76.6 upon 76.6, which makes it approximately 0.2. So alpha value 0.2. Everybody clear? Since alpha is known, I can calculate what is x. X is equal to 100 alpha, which is equal to 100 times of 0.2. Okay, so that makes it 20 moles. So 20 moles of N2O4 is consumed. So therefore, number of moles of N2O4 consumed will be 20 moles. Left is 80 moles. Left is 80 moles, and number of moles of NO2 formed will be equal to 2x in this case. So that makes it 40 moles. So this is the composition. How much is left? How much is used? Okay. So we got the moles already. Once we get the moles, we can easily calculate what is the weight also. Correct? So please check this out. If you have any problem in understanding, let me know. Finished? Everybody done? See the next question. No? I'll give you one more question. Please try this out. For the reaction, for the reaction, 2 moles of ammonia is giving you N2 gas plus 3 moles of H2 gas. Okay. What we need to do is calculate degree of dissociation, degree of dissociation alpha if observed molar mass of the mixture is 13.6. Okay. Please do this and give me an answer. What is the value of alpha? Simple and straightforward. You should be able to do it. First, you got to realize this formula that alpha can be written this way. Second thing, what is the N value? See, N value is the number of products that are forming for every 1 mole of reactant. So here you can see for 2 moles, I'm getting 1 plus 3, total 4 moles. So for 2 moles, if I get 4 moles, so for 1 mole, how much should I get? 2 moles. So that's why the N value here is 2. Second, molar mass of the mixture is given as 13.6. And M naught is the initial ammonia molar mass, which is 17. Okay, clear? So putting these values together, now what will be the alpha value? So alpha will be equal to 17 minus 13.6 divided by 13.6 into 2 minus 1. Okay, this is what you're supposed to get. So that will be like 3.6 here. Okay, sorry, 3.4 here. So that divided by 13.6, so which is coming out to be 0.25 approximately. That is the alpha or the degree of dissociation, or the percentage dissociation is 25 percentage. Okay, so I can put that word also, percentage dissociation. Dissociation is simply alpha 100 alpha, which is 25 percentage. So I hope you guys understood the concept. Dave, any doubt here?
No, sir.
Nitya, any doubt?
No, sir.
Right. Next, before we enter into solutions and understand more details about solutions and their concentration terms, we have another term which we need to learn. I kind of forgot to write that page in the notes. So please, you better take it from here. Okay. That is principle of principle of atom conservation. Okay. Principle of atom conservation. POAC. Okay. This is called POAC. As per this principle, what we are trying to say is that when it comes to the number of moles, right, when it comes to number of particles of any atom, okay, number of atoms of any element remains same at reactant and product side, as long as the element is completely transferred from reactant to product. Okay, for example, let me show you what I'm trying to say. Suppose there is a process which is going on where I have some hydrocarbon, let's say C C3H6, correct? And maybe by some n number of reactions here, correct? So, for example, if you have, uh, let me show you this reaction C2H4 here. C2H4, I treated with X2, I treated with Cl2, then I treated with sodium, correct? After all these reactions, last product what I'm getting is, product like this, correct? Okay, this is the kind of product I'm getting. Okay, this product basically represents C4H10. Let's say this is the product which I'm getting. So many reactions are being done in between this reactant and product. But one assumption what I'm taking here is, okay, the carbon atoms are conserved. Carbon atoms are conserved. Carbon atoms are conserved, which means whatever the number of carbons which are present on the reactant, eventually they will be appearing on the product. Of course, they might be in a different form, but the number of atoms which are present on the left and the number of atoms present on the right will remain the same. That is what is conservation of carbon in this case. Now look into this carefully. For one molecule of C2H4, I have 2 moles. If I take 1 mole of molecule, 1 mole of C2H4, I would have 2 moles of carbon, correct? So suppose if you have n moles of C2H4 here, these are the number of moles of C2H4. Similarly, n of C4H10, which means this is number of moles of C4H10. So how these two are related here? Okay. So these both are related based on carbon conservation. So how would I show that? Please check. If I take 1 mole of C2H4, I would have 2 moles of carbon. If at all I have n moles, I should have 2n moles of carbon. So applying, this is how you write it down. Applying POAC to carbon atoms, which implies number of carbon atoms or number of moles of carbon, at reactant site, will be equal to, okay, 2 times the number of moles of C2H4. I hope that makes sense, because 1 mole will have 2 carbons, so n moles will have 2n carbons. Similarly, number of moles of carbon at product side, that will be equal to 4 times the number of moles of C4H10. Okay, 4 times the number of moles of C4H10. So therefore, since both of them are conserved, the number of carbon atoms are conserved, I can equate that. So 2 times of number of moles of C2H4 will be equal to 4 times the number of moles of C4H10. Okay, so this is what we call it as the principle of atom conservation. Guys, I hope you understood this point. So make sure whatever the number of moles on the reactant side and the number of moles on the product side, both of them are exactly, if they are equal, then wherever they are present in the form of carbon, all of those number of moles together on the left and together on the right, they should be equal. POAC is specifically used whenever we are not aware of how to balance the reaction. So if you are not aware that how to balance the chemical reaction, then POAC will be better useful. I'll give you one more example. Check. Imagine if you have phosphorus P4 solid and it is been reacting sufficiently with O2. Then it is forming, let's say, uh, only phosphorus red here, correct? So P here, P red, correct? And then it is also forming P4O10. Then it is also forming P4O6. And I need to figure out, okay, if the number of moles here is NP4 and NP4O10 and NP4O6. Okay, and I tell you, both oxygen and phosphorus are conserved. That means they are not lost into any other molecule. Whatever the molecules are given, that is where they are present. Remember that. Okay. So in that case, let me first show how the phosphorus is consumed. On the phosphorus side, we can have left hand side we have 4. So I can say that 4 times the number of moles of P4. This is the total number of phosphorus on the left hand side. How they are conserved? 1 time the number of moles of P plus 4 times the number of moles of P4O10 plus 4 times the number of moles of P4O6. This is conservation of phosphorus. Next, let me write conservation of oxygen. 2 times the number of moles of O2 is equal to 2 times the number of moles of O2 here is equal to 10 times the number of moles of P4O10 plus 6 times the number of moles of P4O6. So you can see two equations, whatever the unknown, given in the question, you can use that and calculate from the known values. Okay. So quickly go through it. If you have any doubt, you can ask me now. Okay. Also make a note as well. Okay. What is POAC? Please check. So let's follow this question. 27.6 grams of K2CO3. Everything is converting into this form. All of the carbon is being conserved. So if I write the conservation based on carbon, I can say number of moles of carbon will be equal to same as number of moles of K2CO3, because in that only one carbon is there. And now if you compare the carbons here, how many we have? You have 6 times into 2, so 12 carbons. So 12 times the number of moles of complex, right? So therefore, number of moles of K2CO3, we can write it as weight of K2CO3 upon molecular weight of K2CO3, that divided by, that is equal to 12 times of weight of complex, which is the unknown part what we have to calculate, into molar mass of the complex. So from here I can write weight of the complex is equal to weight of K2CO3 into molecular weight of complex upon molecular weight of K2CO3 into 1 by 12. So weight in this case is given as 27.6. Molar mass here is 698 upon molar mass here is 138 into 1 by 12. After calculating, I'm getting it as 11.6 grams. So please check. Right, this is what it should be. Done. Right. Okay. So this is the first part of mole concept, especially the stoichiometry part. Now see the second part of it. Second part is about concentrations and solutions. Okay. I'll quickly browse through the basic definitions. I'm sure you must have come across this. See, solutions are of three kinds: true solutions, colloidal solutions, and suspensions. If we have homogeneous and uniform mixture of components and there is no phase boundary observed, that means solution is absolutely transparent. Okay. In such cases, we call them as true solutions, like salt in water or sugar in water and so on, acids, bases in water. They're all true solutions. Next, colloidal solutions. Here, it is uniformly mixed. All the components are uniformly mixed, but they yet remain heterogeneous. Heterogeneous means Heterogeneous means it might be uniformly mixed, but there is always going to be a phase boundary between the particles, which means a particle might be little more denser than the other particle. So it is very visible. Okay. For example, a buttermilk. In buttermilk, you can see the milk particles will have a little bit different density than the water particles. So that's why they are clearly visible. So such kind of solutions are colloidal solutions. If it is heterogeneous and non-uniform, that means it is not perfectly mixed and there is a sedimentation happening, then we use the word suspension. Okay, clear? Usually colloidal solutions will be always colored. Suspensions are like, half colored and half of the solution will be transparent because there is no uniform mixing. Our job here is to mainly emphasize on true solutions. Now, generally speaking, a solution is made up of solute and solvent. A solvent will always retain its state in solution. That means if you have adding some components and it is always remaining in liquid state, so the solvent must also have been a liquid state. Okay. And there may be n number of solutes in a solution, but there will be only one solvent. And we can have many different types of solution that includes liquid, liquid solid, solid liquid, liquid gas, gas liquid, solid, solid gas, and gas solid. So basically all three different combinations, which makes it nine different type of solutions. Okay. Our objective main here is to figure out concentrations of true solutions. Now, what is this term means? Okay, that is concentration or strength of the solution means. Okay. Right. Sorry. Am I setting? Yes. So check out. It is about the amount of solute present in the solution. Now, this amount could be defined in various terms, everybody. It could be a percentage composition, a mole fraction, molarity. All of these are different terms. Okay, or normality, all these terms. So now notice, if you have a percentage composition term to be used, that is percentage weight by weight. Okay, percentage weight by weight means how much amount of weight of the solute is present upon the weight of solution into 100. Likewise, if you have percentage V by V, means it is volume of a solute by volume of the solution into 100. It could be weight by volume also, which is weight of solute by volume of solution. Weight, volume by weight also, volume of solute by weight of the solution into 100. So all these are different representations of percentage compositions. Okay. So these percentage compositions are very, very often used in, whenever we have different solutions, right from pharmaceutical industries to beverages, okay, to chocolate industry, uh, all the, all the, what do you say, confectionaries, okay, they all use this type of representation, which is percentage composition. But when it comes to laboratory scale, we will start going into little different mode of identifying concentration or strength. The first one is molarity. That is, how many moles of a particular solvent is present in 1 liter of the solution. We represent that as number of moles of solute by volume of the solution. Typically, the units of molarity includes mole per liter, molar, or capital M, molar. Okay, these are the units that are used. Another term which is used is molality, small m, molality. That implies how many moles of a particular solute is present in 1 kg of solvent. We are trying to refer 1 kg of solvent. So molality is equal to number of moles of solute by weight of solvent in kg. Okay. Units would be mole per kg, molal or molal, m. These are all the units. Next. Mole fraction. Mole fraction X represent number of moles of solute per total number of moles of solution. Okay. So number of moles of one particular solute upon total moles of the solution. Okay. This is for binary. Binary means only one solute, one solvent present. If you have multiple solutes also, does not matter. All of those additions here, you have to do it. And number of moles of that solute, number of moles of that. Check again. So you can see number of moles of solute by total number of moles of solution. Okay. So have a quick sneak on the terms here, everybody. Percentage composition. There are these 4 types of percentage composition. Honestly, you don't have to write it right now. Just if needed, if you haven't written or this is the first time you are watching, just write the formula. That is what is molarity, what is molality, and what is mole fraction. That should be enough. Okay. But try to understand terms very carefully. Okay, what's in the numerator, what's in the denominator.
So on mole concept, mainly only these sums come on like these three and the percentage compositions, right? As well
Now
as
we do
the
have more ppm and all. We're going
yeah,
down the
that's the percentage
normality.
composition only, no? But
Yeah,
mostly
yeah,
it
yeah,
comes
only
on
this.
this only, right?
Yes, yes, yes. All good, guys. Then see, in a similar way, we can have something called parts per million ppm, which is representing how much amount of solute is present in 10 raised to power of 6 grams of solution. Okay, basically how much is present in a million. Okay, usually this type of composition is used when the weight of the solution solute is extremely small amount. Okay, especially when we have to measure the ions present in water. Okay, so fluoride ions, iodide ions. Okay, uh, calcium, calcium ion concentration, magnesium concentration. These are all the ways we represent usually in ppm. And then there is ppb also. Okay, parts per billion. This is b, parts per billion. So parts per billion is used. Parts per billion is used especially when you are discussing something about a bacteria or a virus, correct? So in that case, even such a small composition makes a lot of impact. That's why we need to be able to figure out how much amount of that solute is present in 10 raised to power of 9 grams of solution. Okay. Typically, ppm and ppb are always taken as a weight ratio. Okay. So guys, these are the main terms, concentration terms. Now the next point is about relating this. Okay. So how do we relate the percentage weight by weight and molarity? Check out. Molarity is about number of moles by volume. Number of moles divided by volume, which is represented in liters. Now what if I write it in ml? Okay. So imagine like this. If this denominator was 5 liters, I could also write the term as 1000 ml, sorry, 5000 ml by 1000, correct? So basically my molarity formula is not changing, or the value is not changing. That let the just the representation is changing. So now when I write the same volume of solution in liters in or in terms of ml, I have to just divide it by 1000. So that 1000 will come into the numerator. And now volume of the solution can also be written as weight of solution divided by density of solution. And since this is in ml, it is a CGS system. So I can write weight in grams and density in gram per ml. Number of moles of solute can be written as weight of the solute by molar mass of the solute. And now if you observe carefully, these three terms are making into a percentage weight by weight composition. Correct? So you can see that is nothing but simply percentage weight by weight. That into density, and there is one 10 unit remaining here. So 10 divided by molar mass of solute. So quite often you would be directly given these terms so that you can figure out how to calculate the molarity. Okay. So in such cases, instead of trying to decode everything, we can simply use this formula and calculate. Right, guys? I hope you understood what to do about this one. So we can simply use this formula and do it. Clear? And this is a must do question. JEE mains usually ask this question very frequently. Okay. In every alternate session of JEE mains, you'll always find this question. Got it? Now, let's see another dependency or relationship between molality and molarity. If I want to derive any relation between these two, then how would I get that? Check. First, let me write these two terms. Molarity by definition is number of moles of solute by volume of solution, while molality is equal to number of moles of solute by weight of solvent. This is in kgs, this is in liters. So it's pretty easy to observe that there is one factor common, which is number of moles. So I can write molarity into volume of solution in liters is equal to molality into weight of solvent in kg. So as you equate these two, now I can write this as I can push this volume term to the right hand side here, okay, because this is a weight term here, and I can push this volume term to the right hand side here. So that makes it molarity is equal to molality into weight of solvent in kgs divided by volume of solution in liters. Now see how we'll slowly change the units one by one. First, what we can do, we can write this m is equal to small m into weight of solvent in grams. So the minute I put it in grams, that 1000 will come out in the denominator, and volume of solution in liters. I'll keep that in liters only. It has useful going ahead. It will be useful going ahead. So therefore, this 1000 times of m will be equal to molality into weight of solvent. Now I can write it as weight of solution in grams minus weight of solute. WS means weight of solute in grams. And that whole is divided by volume of solution in liters. Okay, knowing that, if I write this again, 1000 times of capital M is equal to small m into, now let me put it individually, weight of solution in grams divided by volume of solution. Now I'm writing that solution in uh, ml. So if I write it in ml, that 1000 will come into the numerator. That minus weight of solute in grams divided by volume of solution in liters. I'll keep this side of the part in liters only. Okay. So keeping that, I'll get this as 1000 times of m is equal to molality into, notice this one, weight of solution by volume of solution is nothing but density. So that makes it 1000 times of density of solution minus. Now notice something. What if I multiply and divide with molar mass of the solute? I'll just multiply and divide with this term. Okay. So now notice what is happening. Weight of the solute by molar mass of the solute, that becomes number of moles. Number of moles divided by volume, that becomes molarity. Correct? So basically this entire term is converting into a molarity term. Hence, if I write this as molality into 1000 times of density, density of what? Density of solution minus molarity into molar mass of the solute. Okay. Now bring all of this term to the left hand side and that becomes a formula. So molality is equal to 1000 times of molarity upon 1000 times of density of solution minus molarity into molar mass of the solute. Okay. So this is how we'll be using the formula. Again, this is a very frequently used formula. Specifically in advanced exam, you'll always come across this because this is not going to stop here. This formula will be useful in electrochemistry. It could be used in ionic equilibrium everywhere. Okay, it will be used to help in relating molarity and molality. Okay, take a quick look. If possible, make a note of it because this will be good practice for you. Check out what I have done. If you have a doubt, you can ask me. Now, let's work out a relation between molality and mole fraction as well. Okay, molality and mole fraction as well. Let us see how we can get that. So, molality by definition is number of moles of solute by weight of solvent in kgs. Okay, and mole fraction is number of moles of solute by total number of moles of solute into plus number of moles of solvent, right? I'm just taking into a binary case. Okay, let's consider a binary case here. Binary means one solute, one solvent case. Now see how I can play around with this x here. So first I'll reciprocate this. Then I'll get this as ns plus n of solvent by ns, which makes it 1 plus number of moles of solvent by number of moles of solute, which makes it number of moles of solvent by number of moles of solute is equal to 1 by x minus 1. So 1 minus x by x. Okay, this is not x exactly, we call it as chi. Okay, so you can call it as chi there. So then now reciprocate once again. So number of moles of solute by number of moles of solvent, that will be equal to x by 1 minus x. And this I can write it as number of moles of solute by solvent. I can write it as, number of moles of solvent, I can write it as weight of solvent upon molar mass of the solvent. But this is in grams, so that is equal to x by 1 minus x. Okay. Now, if these grams I have to represent in kgs, so I can write this as number of moles of solute upon weight of solvent. Okay, weight of solvent in kg multiplied by 1000. So that is equal to x upon 1 minus x. So I can take that 1000 up, and what is this value converted to? This will convert into molality. So that implies molality is equal to 1000 times of x divided by 1 minus x. Okay, so this is another way of representing molality. Okay, please check. All right, I think I forgot molecular weight of solute here. So I have to multiply that molecular weight of solute. Sorry, not solute, solvent. Okay. So not difficult. I think this is how we can relate all of them. So let me put all the values which we learned just now. Okay. Right from percentage weight by weight. So molarity is equal to percentage weight by weight into density into 10 upon molecular weight of solute. Okay. And now if you know the molality, we can calculate molality 1000 m by 1000 times of density minus molality into molecular weight of solute. Well, if I know these two, or in fact, if I know the molality, I can use this formula, and to calculate molecular weight of solute is 1 minus solute into molar mass of the solvent. So all these are very much interlinked. Okay. Make sure at least you have this one written in your book right now, so that you can take this easy for solving. Yeah? Right. Let me show you one quick question. If I were to calculate the molality given the percentage weight by weight of NaOH and density is given, so I can always use this directly to calculate the molality, right? That is one way. Or you can also use the formulas. Since I'm more concerned about learning out these formulas together, so I'll first solve it by a formula, and then we can solve it just based on the given data. See how we can use the formula and get it. First, try to get molarity because percentage weight by weight is given. So molarity is equal to percentage weight by weight, which is 4 into 10 into density, which is 1.2 upon molecular weight of solute. In this case, it is 40. So molarity is 1.2 molar. Okay. Molarity is given, density is given. So let us use that M here. So M is equal to 1000 times of molarity divided by 1000 times of density minus molarity into mole fraction of the solvent. It is an aqueous solution. Sorry, it is mole fraction of the solute, which is 40. Okay, so which makes it 1200 upon 1200 minus 40, 48. 48. Okay, so solving that, I'm getting somewhere like 1200 by 1200 by 1152. Got it? 1200 by 1152. So let me see how much is the exact value I'm getting. 1152. So I'm getting it as 1.114 or 1.04. This is molar. Have you noticed these values are pretty close? Okay. Now, what does this mean is, whenever it comes to molality and molarity here, correct? This way. Okay. So you can see molarity and molality, as the concentration is increasing, their differences will start increasing. Difference between them will start increasing. Okay. So usually, if you have M here, typically this is how it goes for molality versus molarity. Molarity goes this way. This is for molarity. Okay. So basically, this is a concentration term, and this is the molality term. This is molarity term. Can you see? Both of them converge close to each other when the values are smaller. That means the concentration is closer by. Okay, and this usually happens at a lower concentration term. Okay, so or I can simply write this as M versus sorry, M versus M, M versus M here. Okay, so that is how the molality is changing. Okay, as the concentration increases. Sorry, this is concentration. This is here is a concentration term. As the concentration increases, so that means these two values are increasing, so the gap between them increases, and here gap between them decreases. So this is either molality term or molality term, right? Okay, we got molality, but then sorry, we got molality. Yeah, that's all we require from this question. Now let me tell you, without formula, how we can solve it. As per the question, we know that the weight of solute can be taken as 4 grams when the solution is 100 grams, which implies weight of solvent is 96 grams. So I can use that directly to calculate molality. So that is number of moles of solute is equal to 4 by 40. So that makes it 0.1. Okay. And molality, sorry, weight of solvent in kgs would be 96 into 10 raised to power of minus 3 kgs. Hence, molality is equal to number of moles of solute by weight of solvent in kgs. So, which is equal to 0.1 upon 96 into 10 raised to power of minus 3. Okay, so that is coming as 100 by 96. Correct. So that is exactly 1.04 molar. So this is without using formula, we can calculate that as well. Okay. Next, check out what if I have 0.4 molar aqueous solution taken in a test tube. Find the mole fraction of the solute. Now this time I need to figure out the mole fraction. Now what you could do here, see, molality M is equal to 0.4, or 0.4 can also be written as 0.4 by 1, and relate this as ratio, that is number of moles of solute by weight of solvent in kgs. So that implies if I relate that with the ratio, number of moles of solute is 0.4. Okay. Solute is 0.4. Weight of solvent is 1 kg. Okay. If solvent is 1 kg, I can write this as 1000 grams. So number of moles of solvent will be equal to 1000 grams upon molar mass. Since it's an aqueous solution, molar mass is 18. Okay. So that 18, when you divide, you will get this as 55.5. So which implies mole fraction of solute, mole fraction of solute now can be written as number of moles of solute upon number of moles of solute into number of moles of solvent. So mole fraction S is equal to 0.1, right? So, sorry, 0.4 0.4 upon 0.4 plus 55.5. So which is 0.4 upon 55.9, which I can approximate this to 56. Got it? So 4 divided by 56. So that is coming out to be 0.071. That is the value. Clear? So this is the mole fraction. Any doubt in
Uh,
these two questions?
Sir, how
Yes,
did you
Vijay.
get 18?
Because the question is mentioned that it is an aqueous solution. So the solvent is water. Okay.
Yes, I got it.
See the next one. If the mole fraction is given this time, you have to calculate molality. So in that case, what will I do? So mole fraction given is of solute is given is 10 raised to power of minus 2. See, if nothing is given, you will always consider it to be binary solution. Okay. Now go with the formula that it is number of moles of solute upon a number of moles of solute plus number of moles of solvent, which is equal to, I can write this as 10 raised to power of minus 2 by 1, right? This is by 1. So it can be written as 10 raised to power of minus 2, correct? Plus, I can write this as 0.99, isn't it? Because 0.99 plus 0.01, that makes it 1, correct? Now, if I relate these formulas together, I can say number of moles of solute is 10 raised to power of minus 2. Number of moles of solvent is 0.99. Since 0.99 is very close to 1, I can say it is almost about 1 mole of solvent. So weight of solvent in that case will be equal to 18 grams because solvent is aqueous solution. Therefore, therefore molality is equal to number of moles of solute by weight of solvent in kgs. So number of solute is 10 raised to power of minus 2 upon weight of solvent is 18 grams, which I have to convert that into 10 raised to power of minus 3, that is into kgs. So molality is equal to, so 10 by 18, correct? So that is what you'll have, 10 by 18. So which is 0.55 molal. That will be 0.55 molar. All okay? So you can see here you don't even worry about the formulas. Got it? So instantly, if you do not have time and you are aware of the formula, I think well and good. Especially formula is extremely useful when it is about molarity and molality comparison. In other cases, even if you do not remember the formula, you can directly use the data carefully and figure out the unknown parameters. Now, check it out. Last thing, that is volume dependent parameters will be affected by change in temperature. That is, in case if at all I'm changing temperature, that means I'm calculating concentration at 25 degrees, 35 degrees, 45 degrees, 55 degrees, and so on. Which kind of concentration term will affect the most is the one where the volume is being present, because temperature, I mean, whenever you change the temperature, the quantity of liquid, right, whichever is more volatile, that will start evaporating. So the volume content will start changing. Now, because the evaporated amount will still maybe in the container as long as it does not escape, but the phase has changed. That means instead of being in liquid state, now it is in vapor state. So it heavily impacts the volume. That's the reason why the volume parameters will have a large change in the concentration. For example, this is volume dependent, volume dependent, volume dependent. Molarity, normality. Going ahead, we learn that these are all volume dependent parts. Now, temperature independent. That means irrespective of whatever temperature you operate, their concentration does not change. For example, molality, mole fraction, percentage weight by weight, ppm, ppb, and so on. They are time independent. Okay. Guys, any doubt here?
No, sir.
Well, next. Let us understand what is the principle of dilution. See, if you add a solvent to decrease the concentration of the solution, that phenomena is called dilution. Okay. You're not adding solute, mind you, we are only adding solvent. So during solution, the number of moles of solute remains the same. For example, if I take initial quantity where molarity is M1, volume is V1, then the number of moles of solute will be M1 V1. But then I added solvent to it. This is solvent of delta V volume. So now the final volume has reached as, now the final volume V2 has become V1 plus delta V. Okay. And for that volume, if the molarity is M2, one thing we are sure of that the number of moles of solute here and here will be same. So if I equate these two, I can say M1 V1 is equal to M2 V2 and V2 is equal to V1 plus delta V. Okay, correct. So you can calculate how much volume to be added. Delta V is the volume of liquid or the solvent to be added. Okay, so this is a simple formula that can be used during dilution. So notice it. If you have 200 ml of 0.5 molar NaOH, it is diluted and final concentration is found to be 0.01 molar. We need to find out the amount of water added. So same question here. So you can see initially M1 given is 0.5, M2 given is 0.01, V1 given is 200 ml. So now we need to calculate what is V2 first. So V2 will be equal to M1 V1 by M2. Sorry. So which is 0.5 into 200 upon M2, which is 0.01. Okay. So that makes it 1 liter, correct? Uh, now which is that? So this will go away to 2.5. So yeah, 1. So we are getting this as 1 ml. Please check. Okay. So if I take this as 200 ml into 0.5, 200 ml into 0.5 divided by M2, I have to change the concentration to 0.01. Correct. So we have this as this is given as 0.5 and mole ml is 200 here. This is volume. Yeah. So that divided by 0.01. Sorry. So how much we have? 10,000 ml. Okay. So because on multiplying these two, I will get this as 100 divided by another 1 by 100. So 100 into 100 makes it 10,000. If this is 10,000 ml, so what will be delta V? It will be V2 minus V1. Okay. So that is 10,000 minus 200. So which is 9,800 ml, all simply 9.8 liters. So we have to add 9.8 liters of water into it. Hey guys, I hope you got this. Manav, Kapil, any doubt?
No, sir.
No, sir.
The same fundamental can be applied even when you have mixing of solutions. For example, if you have M1V1 number of moles here, M2V2 number of moles here, and finally after mixing you'll get M3V3. So now M3V3 can be related as the sum of the number of moles of 1 and 2. Okay. Let's use that logic in this question here. So we have 4.9 grams of H2SO4 added to sorry 400 ml of 0.1 molar H2SO4, and finally a 1 liter of solution was made by adding water. You have to find out the new concentration of the H2SO4. So new concentration M3 is equal to, either you write it as M1, I'll write this as this way. N1 plus N2 are the total number of moles divided by total volume or final volume. So here N1 I'll write it as simply N1. Okay, sorry, N1 I'll write it as weight by molecular weight. N2 I will write it as M into V divided by total volume. Weight here is 4.9 by 98. This is one way of representing number of moles. Then 0.1 into 0.4, because everything I'm writing it in moles, divided by total volume. Total volume is 1 liter. So M3 will be equal to, got it? So this goes 1 by 20. Okay. So 1 by 20 is 0.05, plus this is also 0.04 upon 1 liter, which is 0.09 capital M. That is the molality. Please check it out. All okay? Right, guys. So yeah, we'll stop it here now.